Zenglo, thank you for the introduction. First, can I double check? Can you hear me well in the back? Yes. Okay, great, wonderful. Thank you very much. Wonderful. So my name is Manos from the University of Michigan, and I'd like to tell you about our work on how to use phonons and the APW code to calculate phonon-assisted optical processes. I will discuss the simplest way based on perturbation theory, and I will introduce also the work of Marios and Sabia, who we'll hear from later in this school. So today, this is the overview of the lecture we'll discuss. So first, we'll talk about why do we need to consider phonons when we discuss optics. We'll start with an overview then of the optical properties of materials, the refractive index, the absorption coefficient, and then we'll dive into the equations for the theory, from classical theory to quantum theory. Then the main part will be how to introduce the theory of phonons and how they enable optical processes. That will be the main equations. And along the way, we'll discuss applications for materials where it matters. Silicon, as well as other indirect gap semiconductors. We'll discuss metals. We will discuss doped semiconductors, which we treat like metals, and transparent conductors. And I will conclude with presenting the alternative method that you will hear in this school on Friday and Saturday. And I will also give you a few references for further reading. All right, so let's talk about why do we need to study optics with phonons. So this is the band structure of silicon. And if you want to look at optical absorption in silicon, there are many codes out there to calculate the direct optical spectrum. The Berkeley W code, the Yambo code. And so in direct optical absorption, photons give you energy, visible photons about 1 or 2 eV or so, but they don't carry much momentum. They move at the speed of light, so the momentum of photons is very small. So in this diagram, in the band structure diagram, direct optical absorption happens vertically, the same K point. And so if you want to study direct optical absorption, you see you can find great agreement with experiment for silicon, including the effect of excitons that you also learn later in this school with the Berkeley W code, as well as if you want to put the temperature broadening of the state, if you want to put the lifetime of the states with temperature, you can see you can match experimental spectra pretty well, as you see in these references. However, if you notice, this good agreement happens in the ultraviolet, right? All these photons are above the visible spectrum. Why? Because the minimum direct bandgap of silicon, the minimum energy you need to have this vertical transition is 3.4 electron volts at the gamma point of the beam zone. However, silicon has an indirect bandgap of 1.2 eV. And so if you want to look at the absorption of visible photons with energy between 1.5 to 3 eV, that's a visible spectrum, it is impossible in silicon in a direct way. If you don't have phonons, silicon should have been transparent, right? But it's not. Silicon is the most successful solar cell material precisely because it absorbs in the visible, right? And so the way it absorbs is because you need some extra momentum to enable transition across the indirect bandgap, and that is coming from the phonons. So the photons give you the energy of, again, visible photons 1.5 to 3 eV, and the momentum, which can span the entire Brillouin zone, can come from the phonons, and that enables the indirect gap transition, and that explains why silicon does absorb visible light and solar cells operate. Okay, so that's why we need it. It's there in even the most basic solar cell technologies. All right, so to describe the optical properties of materials, we need to first start with coefficients, so we can put numbers in the data. So if you want to describe how light propagates, how it gets reflected on surfaces, we need to talk about the refractive index between materials. And if you want to describe absorption, we want to quantify it using the absorption coefficient. What happens is that if you shine light into an absorbing material, the intensity of the beam decays exponentially as light propagates inside the material. And how fast the light will attenuate is given by the absorption coefficient in units of inverse length. So if you invert it, it tells you what is the penetration depth, how deep inside the material light will propagate. If you have a strong absorber, you expect absorption coefficients on the order of 10 to the 5 to 10 to the 6 inverse centimeters, which corresponds to an absorption depth of about 10 to 100 nanometers, so 10 to 100 nanometers. And so I can start with a few tens of atomic layers thick. All right, so our goal is to quantify the refractive index and the absorption coefficient starting from atomistic calculations. So first, a little bit more about the optical coefficients is that in order to describe both propagation and absorption, we need to go to complex optical coefficients. So the complex refractive index has the real and imaginary part. The real part is the propagation, the imaginary is the attenuation. And the same thing for the dielectric function. It has a real and imaginary part, again, the real propagation, the imaginary absorption. These optical constants are connected with each other through these relationships. And of course, you can invert them to find. So if you know epsilon, epsilon2, you know n and k, and vice versa. You can invert these relationships. And the coefficient kappa, the extinction coefficient, in this case is dimensionless. It's like a refractive index. However, you can give it units if you multiply by 2 omega over c, and that's how you find the absorption coefficient with units of inverse length. Okay. All right. So how do we find these coefficients? If you use classical theory of free metals and free electrons in metals, and that will be the Drude model, you can find the optical loss of electromagnetic radiation by looking at the oscillatory behavior of free electrons when you apply an oscillating electric field. Okay. So it's Newton's law, mass times acceleration is equal to the force coming from the external field, but we also need to apply the resistive term, the phenomenological Drude term, which causes the dissipation, the loss. Okay, so the energy is transferred from the electrons to the phonons. So this way you can get the DC conductivity, the known result from how to connect the properties of the materials to the macroscopic conductivity. Now, if you assume the electric field to be oscillatory, you can find the loss as a function of frequency, and that's how you find the absorption coefficient for a classical material. Again, it's given in terms of the density of the electrons, the effective masses, the refractive index, and the crucial parameter is tau. Tau is a phenomenological parameter. It's the mean free time between collisions, the average scattering rate for electrons. And with classical theory, it's a phenomenological parameter. People fit it to explain experiments, but there's no ab initio theory to describe it. And also, as you see here, classical theory works for materials that do have free electrons. If you don't have free electrons, you can't use classical theory. Classical theory doesn't know about bands and band gaps. So for that, we need to go to quantum theory. Okay. So now we assume we have electrons that live in a solid, which has a band structure, and we use first order perturbation theory to calculate how light attenuates in this material. We start with the unperturbed state, which is your DFT or GW wave functions and eigenvalues. And we perturb them with the electron-photon Hamiltonian. For a bulk crystal, we don't want to work with the position gauge, we work with the momentum gauge. So we use the vector potential dotted with the momentum gauge to find the electron-photon interaction. And because we use the potentials, we want to switch the velocity gauge because this way the momentum operator does not commute with the non-local part, so the velocity is a better description for the gauge. Now, how do we find the absorption rate? That's where we go to Fermi's golden rule. The probability of absorbing a photon and transition from state I to state F, the initial to final state, the probability per unit time, is equal to 2 pi h over h bar, the matrix element of the perturbation Hamiltonian between the initial and the final state, and last a delta function to conserve the energy. So density of states factor here. What are the initial states? You have an electron in state I with momentum k, it absorbs the photon and goes to some other band j and k, right? So from the valence to the conduction band. We can quantify the power being absorbed by summing up all the photons that get absorbed from every initial to every final state times the photon energy. At the same time, we can also quantify the power coming in from our light beam. So we know how much power is being absorbed, how much power is incident, and if we divide the two, we can find the absorption coefficient, right? So I give you the equations here to find the energy absorbed per unit volume divided by energy flux, and you arrive at this equation, okay? So what is involved? It involves three factors like the refractive index, speed of light, the frequency, charge of the electron. And then because this is direct absorption, this is still about direct optical absorption. we have a single sum over the Brillouin zone. We're looking only at vertical transitions over between initial and final bands. The occupation factors here ensure that you go from occupied to empty states only, so not transition between two empty states or two completely filled states. The matrix element involves the velocity matrix elements. These are the same elements as the transport calculation, except they go from one band to another. These are interband matrix elements. This is a velocity. It is a vector quantity, so you need to dot product it onto the polarization of your light. So the absorption coefficient is a vector quantity that has components along the directions of light polarization. And last, a delta function to conserve energy. So if you do this sum, the delta function will become a density of states, and you'll be able to get the absorption coefficient. I also give you the equations for the real and imaginary dielectric functions. So here they are. The dielectric function, again, just a different prefactor in the front because we have some different coefficients to multiply. And if you want to find the real part, now the imaginary and the real part are not independent of each other. Because of causality, they must satisfy the Kramers-Kronig relation. So if I know the imaginary epsilon2 for all frequencies, the important part is all frequencies, I can perform this integral and I will find epsilon1 for a given frequency, right? And so if we have a broad spectrum, we can integrate and find the real part. And here's the equation. Once you apply the Kramers-Kronig to the equation you see here for epsilon2, you find the equation for the real part, the epsilon1. And from that, you can then go on to find the refractive index and everything. Okay, so far we're talking about direct absorption. Okay, so the sum is over only one wave vector index, which corresponds to the wave vector where the vertical transition takes place. So now let's put phonons. In this case, we have our initial state. The electron is in the valence band, and it needs to absorb both a photon and a phonon. So we have now two perturbations. So we need to go to second order perturbation theory and evaluate the combined effect of coupling to photons and phonons. Going back to Fermi's golden rule and going to second order, we see again 2 pi over h bar, a delta function to conserve energy. And now our matrix element is different to account for the fact that the Hamiltonian is going to second order. It involves this sum over intermediate states M and this energy denominator so that the units match as well. Okay. So for the Hamiltonian is the sum of the electron-photon plus the electron-phonon interaction. And so the terms we want to keep are only the cross terms that involve one photon and one phonon. We don't want to have two photon absorption. We don't want to study two phonon scattering. We just want one photon and one photon to describe the absorption. So here's the term, 2 pi over h bar again, the delta function to conserve energy. And then our matrix elements, we have two terms which differ in the order in which the photon and the phonon interact with our electrons. Okay, both of them involve sum over intermediate states that can extend over all bands. All right. So following the same steps as before, we can transition from this fundamental equation from the rate to the absorption coefficient for materials. Okay. So this is the end result. If you want to find the absorption coefficient for phonon-assisted optics, now you need the following elements. Again, we have this prefactor, which is again optical constants. We have a delta function to conserve energy. And now we have to account for the fact that your initial electron at state I absorbs the photon and also absorbs or emits a phonon and ends up in state J. Okay, so the phonon also enters the energy conservation. Right? So this delta function conserves energy when the electron absorbs a photon and absorbs or emits a phonon. And the key element here is the matrix element, right? Now we generalize it because now we don't have just a velocity matrix element. Now we need to factor in the electron-phonon coupling matrix elements G that we've seen in previous lectures. And because we have two paths, depending on which order the velocity or the G matrix elements are taken into account, we have two terms inside the sum. And we have to first sum them and then square them, because we have to account for interference between these two terms. Right? Again, lambda is the light polarization. And so, a key factor here is that we have to sum over the wave vectors of the initial state and the wave vector of the phonon, right? So now we're doing a double sum over the Brillouin zone, which again brings up the challenge that we've seen earlier about the transport and spectral activity. We have this double sum over the Brillouin zone. The matrix elements involve energy eigenvalues, the velocity matrix elements, and the electron-Phonon Cauchy matrix elements. And last but not least, we need to account for the occupations to ensure that we go from occupied to empty states, and that we also take into account the phonon occupancies where the population of phonons also come in. Okay. One note that when we sum over intermediate states M, we sum over both occupied and empty states, because this is just a perturbation theory expansion. So the fact that the states are occupied doesn't mean that you don't take them into the sum. Okay. So these states, so graphically, people denote this diagram like this. So this intermediate state M, the electron never truly occupies this state, right? Energy is conserved only between the initial state and the final state. The intermediate state does not conserve energy, and those denominators are generally not zero. Okay, if you are below the direct bandgap. All right. So again, the challenge with Phonon-assisted optics is that when you look at direct optics, you have a single sum. You sum only vertical transitions. When you look at the Phonon-assisted process, you have a double sum. The initial state can be any state in the Brillouin zone. The final state can be any state in the Brillouin zone. You have this double sum. And that is very expensive. I'll show you here what we need to do. So if we want to get the spectrum of silicon with a resolution of about 30 millieV, that corresponds to a Brillouin sampling grid of about 24 by 24 by 24, right? This is a double grid for both the initial and the final state, which gives about 200 million combinations of initial and final state wave vectors. So, oh, louder? Okay, I can do that, sorry. Yeah, if you speak louder, please just do like this and I will, yeah, all right. Okay, so doing one of these calculations for the matrix elements, easy. You can do it on your laptop in 5 minutes. Doing 200 millions of them, not possible, even of big supercomputers. And that's where the techniques that we learn in this school come in. The solution is to interpolate the necessary quantities using maximally localized Wannier functions. So, as learned from Professor Marzari on Monday, we can use the maximally localized Wannier functions to interpolate the energies, the band structure, and the optical matrix elements throughout the Brillouin zone. That happens when you look at interpolate a quantity that involves only one wave vector index. It's a single, the K index only. But crucially, the most important quantity is the Electron-Phonon matrix elements. And that's where the EPW code comes in, because it can interpolate the matrix elements from any K to any K plus Q throughout the Brillouin zone. It's a double sum that we want to tackle. And doing this, we're able to get calculations for the optical spectra of materials. So here's the first result we got for silicon back in 2012, where you see that now, by doing Phonon-assisted optics, we see the absorption onset of silicon at the indirect bandgap. So you see how the value of around 1.1, 1.2 eV, we see that we do start to see absorption. And I want to note here that back then, the calculations for studying how bandgaps depend on temperature were still being developed. So in order to compare to experiment, we just had to manually shift the onset of the absorption to match experiment, both because we didn't have enough accuracy in our calculations to match experiment, also because we were missing the 0-point corrections and the finite temperature effects due to phonons. But once you correct for the onset, you see how we get this beautiful agreement with experiment for the absorption spectra of silicon near the onset. And most importantly, by summing over the entire Brillouin zone, all possible combinations, we're able to find how silicon absorbs light in the visible spectrum. That was the first time that ab initio theory was able to calculate how silicon absorbs visible light. Again, we had to shift the onset to match experiment, but besides that, you see, we have this amazing agreement over 5 orders of magnitude with experimental data that were back from the 50s. So after decades, finally we were able to enable this capability, and that you'll be able to use tomorrow in the examples, and you learn more about further developments that happen since that you can use to also account for the effects of temperature dependence of band gaps, etc. So since then, we applied to many other intergap semiconductors. So I'll give you a few examples. For example, cubic silicon is well studied, as we showed you earlier, but recently people have been looking at other polytypes of silicon. What happens if I take silicon and modify its structure, basically the stacking sequence of its tetrahedral layers? That can be a way to engineer the bandgap to make it smaller, but also we can further break the symmetry and increase the absorption. So as you see, when we have cubic silicon and compare the 4H silicon does absorb stronger in the visible spectrum, and that can give you better efficiency for solar cells, particularly for solar cells that are thinner. So you can reduce the thickness of solar cells of silicon by a factor of almost an order of magnitude and still get the same efficiency with less material. So this is the work by Xiao, who you'll get to meet tomorrow at the hands-on workshop, as well as the tutorial. Another place where we can apply calculations is for the silicon carbide, where we can study again various polytypes and see how they absorb light in the visible spectrum. Again, we see that we get a reasonable agreement with the experiment and understand how the origin of the various features affect the optical spectra, but also we can predict the properties of new polytypes that haven't been measured yet. So that's another way to use predictive theory to predict the spectra of new materials that may not have been synthesized or characterized yet. Before we move to the next subject, let me make a quick comment. How do experimentalists know what is the bandgap of a material? And one way to do this is with optical measurements, right? So you shine light. Below the bandgap, there should be no absorption. Above the bandgap, absorption kicks in. So when you see this onset, you say, there's the bandgap. Unfortunately, experimental data are never that clear. You don't see this sharp step onset. What they see curves like this, right? So how do you find the bandgap in this situation? The answer is you do a so-called Tauk plot analysis. How does it work? We know that when we have a direct absorption, the absorption coefficient increases as you go above the bandgap. So when the photon energy exceeds the bandgap, that's when you have this sharp onset. And the functional form is a square root form. It goes like 1/2 power. So, and there's also an omega in the denominator. So if we move this omega to the other side and square the whole thing, we should find a straight line, right? The absorption times photon energy squared should be a straight line with respect to photon energy, and the intercept with the x-axis is the bandgap. And that's what you see here. So here's an example for tin selenide. The material has both an indirect and a direct bandgap. So if you take the spectra, multiply by the photon and square, you get this kind of spectrum. And then you take this straight line portion, and the intercept will tell you what the bandgap is. Now, that is for a direct bandgap. But if your bandgap is indirect, the functional form is different, right? Because now you have two densities of states to compare, the density of states of the valence and the conduction band. The functional form involves a square in this factor here. So now again, if I move my omega to the other side and I raise not to the square but to the 1/2 power, I will get again a straight line. But if I extend to 0, it should give me the indirect bandgap. And that's what we do here for tin selenide. Again, and that's how you see that you try to find this straight line portion and you take it down, and that's how you find the indirect bandgaps of materials. So in this case, we're able to quantify what is the indirect gap and the first direct gap of this material. Okay, so that's how experiment does it. And that's what we did for a new semiconductor, boron arsenide. Boron arsenide looks like gallium arsenide. It is a zinc-boron crystal consisting of 1 boron and 1 arsenic atom. It got a lot of attention back in 2018 because experiments were able to first synthesize crystals of this material. Before that, one had powders. And they verified theory predictions that this material should have an ultra-high thermal conductivity. It is second only to diamond. Diamond is the best semiconductor. Boron arsenide is the next one. So back then, it was a very new material. And so we started right away to study its properties. RGW calculations find that it does have an indirect bandgap of 2 eV, followed by a direct bandgap at 4 eV. And so in collaboration with a group of Professor Gang Chen at MIT, we did calculations for the indirect and the direct bandgap. So you see here the absorption coefficient to the 1/2 power for the indirect gap and to the square for the direct bandgap. And by looking at the intercepts between our calculations and experiment, we're able to verify the experimental magnitude of the bandgap, both the direct and the indirect one, and explain the optical spectra that they measure in experiment. So that's what we do for materials with a bandgap. However, there's another more class of materials where phonons matter, and that is materials with free carriers. So let's start first with metals. Because when you have free carriers, there is one more term in the absorption. Materials can absorb light by having electrons go from a valence to a conduction band, as we discussed before, but they can also absorb light when the electrons oscillate and lose their energy to resistance, to phonons. Okay. So this is again back going to classical physics. The electric field accelerates the electrons, and as they accelerate and decelerate, their energy becomes heat. Okay. So this is how you will find the loss, the imaginary part of epsilon, coming from the resistive loss. This is a conductivity problem. It's an AC conductivity problem. So to find the loss, we use the value of the DC conductivity, but we modify it for finite frequency omega using the scattering time and the frequency of the electric field. So if you combine the terms, you see, if you look at the noble metals such as silver, gold, and copper, you see that we have all terms play a role. We have both direct absorption above the onset of direct absorption. Even though the material has no bandgap, there's still a sharp onset. We're looking at the first allowed vertical transition. Okay, and so for silver, that's in the UV. That's why silver is colorless. For gold, it is somewhere in the yellow part, and that's where reds and yellows are reflected from gold, and here's this nice color, while shorter wavelengths get absorbed. And the same for copper, that's why it has this red coloration. If you look above the onset, direct terms dominate. If you look at below the onset, that will be infrared photons, and we find that both the phonon-assisted contribution as well as the DC loss are comparable, and you need to account for all of them to explain the data you see from experiments. So you see there's a very broad range of experimental data. The reason for that is because samples have different quality. So the scattering time across samples varies, depending on the grain size, on impurities, on thickness, etc. But with theory, we can find what is the fundamental limit to the absorption, and we see again this good agreement with experiment. And tomorrow you have the chance also to practice doing calculations for metals, particularly for silver, and Xiao will lead the discussion. Speaking of free carriers, there is one more class of materials that do have free carriers, and that is doped semiconductors. We discussed earlier that if you have a material with a bandgap, then light can't be absorbed unless it has enough energy to go from the valence to the conduction band, right? Materials are transparent for light below their bandgap, unless they are doped. Because once you dope the material, in this case, silicon is doped N-type, you will have some free electrons right here in the bottom of the conduction band. And those free electrons can absorb light and go to higher conduction bands, right? They can absorb light in a direct way to go from the lower conduction to the next conduction band. They can absorb the light indirectly through the assistance of a phonon that gives extra momentum. And they can also have a resistive loss that can be accelerated and decelerated, and that the energy of the light becomes heat through Joule heating. And so that's what Xiao did in his work. Now, these are the spectra of silicon. Notice this is the infrared range. All these energies are below the bandgap of 1.2 eV. We're looking at infrared light. And as you see, doped silicon does absorb. And all of these terms you see here play a role. The direct term, the phonon-assisted, charge impurity assisted, as well as the resistive term. And if you put them all together, you get this line that once you compare to experiment, you see they're in excellent agreement both for N-type doping by electron as well as P-type doping from holes. And one comment here is that for holes, you see this monotonic behavior looks very boring, the spectrum, just a straight line in log scale. And you tend to think, oh, there must be like only one term. It turns out that you have many terms, all of them being comparable to each other. And the net effect is the combination of all these direct, phonon-assisted, and resistive terms that give rise to this very simple and monotonic behavior. So if you'd like to learn more about this, you can read about this in Xiao's publication, and you can also ask him in person during the tutorial session. Another case where free carriers matter is for transparent conductors. Now, I mentioned again that if the photon does not have enough energy to cross the bandgap, it won't be absorbing the material. And there are cases where we want that. Suppose you want a material that has high conductivity, but at the same time being transparent. Well, insulators are not conducting, even though they can be transparent, right? On the other hand, metals do conduct, but they're opaque, like silver or so. So what's the best way to go ahead with having both conducting and transparent behavior? That tends to happen with oxides, such as tin oxide, which is doped with electrons, but has a wide bandgap more than 3.5 eV. So the bandgap is transparent to photons, and the free electrons give you conductivity. However, those free electrons can still absorb light and go to a higher conduction band. And you see there's a fundamental connection, fundamental limit between having enough electrons to conduct, but at the same time, those free electrons will cause some loss. Again, this free carrier absorption. So went ahead, that was work we did a few years ago, to quantify what is the fundamental limit to the absorption conductivity balance in N-type transparent conducting oxides. And so we're able to get values that explain how these materials absorb light. In particular, you see, fortuitously, these materials are least absorbing in the visible. So that's what we like to see, and that's what makes these materials very successful commercially. So if you'd like to learn more about these applications for transparent conductors, you can read about these works, and also happy to answer questions as well. All right, and before I conclude, I want to discuss, just barely introduce two alternative methods that you will learn in this school about how to calculate optical properties that go beyond this second-order perturbation theory and in fact overcome many of its limitations. The first method is by Dr. Mario Zacharias, and this is the special displacement method. So instead of using the unit cell and doing second-order perturbation theory, what you can do is you can create a supercell that has it's a multiple of the fundamental cell of the crystal, and but you will displace the atoms according to a special linear combination of the phonon modes. And Marius will discuss to you why this particular combination and how to build it. But by doing that, you incorporate the effect of phonons in your initial structure. So your initial structure has the phonons already incorporated. So then what you need to do is just first order perturbation theory, like direct optical absorption between the valence and conduction band. There's some beauties with this method. First of all, it avoids the divergence that we see above the direct bandgap that we have in second order perturbation theory. You won't need to obtain Wannier functions, right? This would be a direct calculation for a big supercell. It also incorporates the temperature dependence of the energy eigenvalues, the bandgap, this Urbach exponential tail. These are naturally coming in from the calculation. Another beauty of this method is that you can generalize it to other functionals, like hybrids, like TFT plus U, or anything you can think of that may not have implementation in density function perturbation theory. And Miles will talk more about this on Friday, and you can also read this paper article for his work. Another method you learn about this school is developed by Sabia, and that is the quasi-degenerate perturbation theory. And the idea here is that you will use the electron-phonon interaction to mix states that are within an energy range from each other. And so the resulting states will be modified by the effect of phonons. So their wave function will be modified to incorporate the electron-phonon interaction. And again, since you incorporate the phonons or your starting wave functions, now all you have to do is first order perturbation theory. You just do direct optical absorption. And again, you see this amazing agreement with experiment, both for the Phonon-assisted regime for silicon, as well as above the direct bandgap, you don't see divergence, and also this great agreement near the onset, including the effect of temperature dependence. And so Sabia will discuss more about this method on Saturday, and you can read more about his very recent publication that just came out a few weeks ago. All right. So if you'd like to learn more about optics and how to connect coefficients to measurements, I recommend the first book by Mark Fox. It's a nice review from the Master series, as well as the this is an older textbook by Bassani and Pastori Paravicini, amazing explanation of the connection of atomistic properties to optical coefficients, as well as recent publications, both about the code and the results. And we would like to acknowledge the developers that work on this code together, in particular Xiao, who you will meet tomorrow and learn about the tutorial, and collaborators, and all the work we've done together. So again, thank you for your attention and happy to take your questions. Thank you very much. Thank you, Manos, for a very nice lecture. So, this one. The first one. Okay, great. Thank you. This is still on, right?
Okay, now let's we have time for questions.
Right, thanks so much. Oh,
If you go back to slide 17.
17. Sorry for getting rather dizzy. 17, yes.
Yeah. Sure, you like to say about, I believe, changing the structure of your system to break symmetry. Can you explain what that is?
Yeah, so what happens is that silicon has many polytypes. So you can imagine silicon have this structure, right? We can think of it as hexagonal planes stacked in a sequence. So cubic silicon has a stacking sequence of A, B, B, C, C, if you think of it as hard spheres. The 4H silicon has a different stacking sequence. It's like A, B, B, C, C, B, B. So there are many ways to stack the atoms along this direction that will give different polytypes, hexagonal, cubic, etc. A material where this is very common is silicon carbide. Silicon carbide, this stacking sequence costs very little energy, so there are numerous polytypes. For silicon, this has been developed very recently, the 4H silicon. If I make a small parenthesis, it's been very important. Why? Because 4H germanium, not silicon, but germanium, has a direct bandgap and can emit light. And that is technologically very, very important because you can integrate a material that emits light directly onto silicon. So silicon does many things wonderfully, but one thing that it cannot do, it cannot emit light. And so being able to integrate the 4H polytypes on the cubic ones would have tremendous technological importance. So that's the context of looking at different polytypes of silicon. And yeah, the band structure can be in principle completely different. So we do see a small reduction of the band gap, but we also do see a stronger absorption because of the broken symmetry. Light gets absorbed but phonons help break the symmetry, and that's what allows the transition across the band gap. So anything that breaks the symmetry helps the absorption. Potentially hurt the conductivity, but the absorption definitely gets improved. Thank you.
I have another question. I know other people behind me probably have more questions too. Could you go to slide 19?
Slide 19.
So you explained how you can express a linear relation between the absorption spectra and the energy difference. Can you explain why for the indirect absorption, straight line isn't as prevalent as, say, the direct absorption?
Yeah, so in this particular case, maybe the samples, I'm wondering if it's not as good quality. So you see here, in the ideal material, this should have been a straight line all the way to 0. However, you see there's some residual absorption below the band gap. This is the so-called Urbach tail. It comes because of disorder effects. That can be defects, that can be even phonons at finite temperature. And so this non-linearity is kind of like hide the onset. So you see, when you look at the direct spectrum, this Urbach tail gets like suppressed. But if you take the same spectrum and just process it, you see this Urbach tail comes and becomes more prominent. And so in materials which are very defective, it's hard to measure the bandgap because these tails tend to be very, very long and very strong. So in this case, it's harder to see the bandgap. So maybe in this case, there are lots of defects that kind of hide the onset. While if you remember, this is the boron arsenide. So this is experimental data, and you see these are much cleaner in terms of the onset. So this is single crystals, high quality samples. That's where you see it more clearly. So I think maybe the samples that kind of hide it.
Okay, thank you so much.
Thank you.
Other questions?
Right. So, in the case of classical theory regarding phonons, I have also seen people adding a Lorentz term to the true term. So, why weren't you adding the Lorentz term?
I'm not familiar exactly with the equation. I suspect that this is like a Lorentz term, right?
The actually has the oscillator strength and stuff also. Then there's it's slightly different because it's centered around the phonon frequency.
Yeah, I'm not familiar. Maybe we can discuss afterwards. If we can, yeah, I'm not familiar with the equation you're describing, but yeah. Since you mentioned Lorentzian, I can make a quick comment also that nothing that people do sometimes is that these delta functions need to be broadened, right? We don't have delta functions in calculations. So then the code gives you two options to broaden them either with Gaussians or with Lorentzians. So that's another place where Lorentzians can enter the calculation. So I think physically Lorentzians are more appropriate, but numerically they're more, they have longer tails. So I think Gaussians is an easier way to get more sharp optical spectra. But I just make this comment with the opportunity. Thank you.
We have other questions?
And there's one in front here. After two.
Okay, so if you go to slide 15, so I have a question regarding the optical response statement. So in experiment, you have done it at certain temperature, and using DFT, like in DFT, you're supposed to do it at new temperature. So what kind of calculation have you done to put in?
Great question. So temperature has many effects, as we'll hear about in this school. So in our case, the temperature we put in is coming in the phonon occupation numbers, right? So this is the one that we took into account for that calculation. High temperature, more phonons, strong electron-phonon coupling. However, temperature has many other effects, including lattice expansion. Crystals expand, so you need a new lattice constant. In the case of silicon and ceramics in general, that is not a very big factor. For metals, it is. For insulators, not so much, or ceramic materials. But another more important factor is those eigenvalues. The bandgap depends on temperature in general. And so phonons renormalize the bandgap, the eigenvalues, as we saw in lectures about the ARPA spectra that show these kinks once you put phonons. So that is the biggest contribution that is missing from our calculation here. So at the time when we did this work, the theories were not developed, the codes were not ready yet. So we went and just corrected for this temperature dependence by applying a rigid shift just to shift the onset to match experiment. Another catch I want to say here is that with typical methods like hybrid functional or GW, we don't tend to have the accuracy to match the spectra so well, right, the onset. Because you see, we're down to the few millivs, tens of millivs. So that's another thing to keep in mind as you look at the spectra at that kind of scale as well. Thank you.
When you were talking about the alternative methods, the first one is the special displacement method. If we use a drop semiconductor, for example, and we impose the linear combination of one of the phonon modes, we might actually enhance the phonon assistance by a certain significant amount at some point.
That's a good question. So you say if we apply this method for doped semiconductors, right? So in principle, you should get the same answer as the perturbative one for as long as you are below the threshold for direct transitions. I can think of some challenges. So an advantage of the perturbation theory is that because you use the unit cell, it's easier to handle cases where the Fermi surface is small. Right? So if you have a doped semiconductor, you only populate a small fraction of the brilliant zone. So there you need very fine phonon wave vectors, order of 100 by 100 by 100 grids. Those are easier to handle with perturbation because you just do many calculations and interpolate on this grid. With the displacement method, you need very large cells to capture these very long-range phonons. And maybe that's a case where the perturbation theory would work better for the effect. But the special displacement method has other advantages, as you see here. So depending on your application, you may prefer to choose one or the other method for efficiency, for practical efficiency. But conceptually, you should get the same answer.
Oh,
You mentioned the Gaussian and Lorentzian problem.
Mhm.
So how do you know the lifetime or the width that you should use?
Great question. So for practical calculation, you are right that this line width should be determined in principle by the lifetime of electrons at those states. So what you could do, you could actually calculate the imaginary part of the self-energy of electrons at those states due to the effects of, say, electron-Phonon interaction for sure, but also maybe electron-electron interactions. You have many possibilities for scattering. For practical calculations, if you don't want to explicitly evaluate this effect, and by the way, this is what they did in this work. So in this work, you see here, the work by Marini, back in 2008, he applied electron-Phonon coupling to see how the states broaden as a function of temperature. And so the Gaussian broadening he used in these cases, or Lorentzian, I'm not sure, I can't recall right now, is the lifetime of the state from electron-Phonon coupling. So that's something you can do. You don't have to do this in practice. Well, one thing you could do is you can choose the resolution you want for your spectra. And then you choose, say, 0.1 eV. Maybe it depends on the problem you're looking for, right? For example, if you look, in this case, we had the resolution of 30 millieV, good enough for our purposes. But 30 millieV here is 2 cores. So here we went even finer resolution. So depending on your application, depending on what features you're trying to resolve, that sets your resolution. And once you set your resolution, that determines, sorry, let me go back, it determines the density of the grid you need to go. So of course, finer resolutions, it means you need a lot more K points to get a continuous band structure, the continuous density of states. Otherwise, you have this like hair comb and the spectra will come out a mess, right? So the two of them are connected, so in that sense. Yeah.
We can take a couple of questions from Zoom audience.
There's a more practical question. It's about this FSD parameter of the PRL.
Oh, yeah.
Is this parameter needed or useful for optics calculation and in which cases?
Great question. Thank you very much for the question. Yeah. So I think Xiao will discuss more about the practical aspects tomorrow in his tutorial. I was going to say that yes, you don't need the FSD parameter because that, for example, in this situation, sorry, the right slide. In this situation, we're looking specifically for the onset of the absorption for silicon. So we look at photon energies, up to say 1.3 eV. So with photons of just 1.3 eV, that means that you will excite from near the top of the valence band to